as Zcash SNARG without setup. This is because independently, any proof system that is either succinct or zero knowledge in oracles, that's a bit of a different story. Anyways, in the last, at this point, 10 years, we've seen extraordinary progress in cryptographic foundations, efficient constructions, implementations, and in particular applications of Zcash SNARG. That's why we're gathered here today. One of the reasons. In particular, one of the applications comes about in a peer-to-peer setting, where through a new generation of consensus protocols, we've built a number of payment systems, okay? And while it wasn't clear at the very beginning, pretty soon it became useful and powerful to use Zcash SNARGs in a peer-to-peer statement to make statements. And now, if you really think of the ecosystem, you can think about it as built on two pillars, okay? The consensus mechanism to agree on events, and Zcash SNARGs that are there to help us make statements about events in a way that is either private or highly efficient, okay? So basically, one way or the other, Zcash SNARGs are here to stay, okay? At least in this peer-to-peer setting. So in this talk, I want to ask a question, which is, okay, Zcash SNARGs are really here to stay. But let's maybe take a sort of scientific long-range view. Which Zcash SNARGs are we going to use, say, in 100 years, or 200 years, right? Which constructions are going to withstand that long of a cryptanalysis? And I want to mention that we actually have a shortage of options. And in particular, most of the efficient Zcash SNARG constructions rely on the hardness of extracting discrete logarithms. And in fact, even more, right? We rely on much stronger types of assumptions, such as knowledge assumptions. And all discrete log-based constructions are, in fact, insecure against quantum adversaries. And if we are to extrapolate the excitement and investment and activity in building quantum computers, may expect some amount of quantum computation available to at least nation states in the next few decades that might break this type of constructions. So if we are to build long-term public infrastructure using Zcash SNARGs, then at the very least, a necessary, maybe not sufficient, a necessary condition would be that we should be interested in post-quantum Zcash SNARGs, okay? And most Zcash SNARGs that we know of today are actually not such. So what do we do? So first, let me give you like a one-slide summary of what we know about post-quantum Zcash SNARGs. It's just one slide because we don't know too much. There is a very beautiful but initial line of research in SNARGs that are based on lattice problems, okay? So we know how to construct pretty good, actually very good, pre-processing Zcash SNARGs, okay, based on knowledge assumptions on lattices, okay? The one caveat of this line of research is that they are not publicly verifiable. They're so-called in the designated verifier setting. So you need some sort of secret to verify the proof. Okay, so these are not the kind of proofs that you post on the blockchain and anybody can verify. They're kind of specialized to a particular verifier. Or in the public setting, we have argument systems that have sublinear proof size, square root in the circuit size, but they're nowhere near the type of asymptotic and certainly not concrete succinctness that we would like. And that's it, actually. These are all the lattice-based SNARG constructions that I'm aware of. In fact, I would encourage you, if you are interested in lattice-based cryptography, I think this is a very, I believe it should be a pretty well-motivated and a well-motivated line of works that probably there's much more to be said in terms of constructions. So the other approach to construct Zcash SNARGs that are post-quantum relies on just using basically almost no cryptography, like a minimal amount of cryptography. That's just cryptographic hash functions. And that's what I want to tell you about today. Okay? So there is a framework that actually should not be new to you, but I'm going to cast it within, today I'm going to present it from the perspective of post-quantum cryptography, which achieves post-quantum Zcash SNARGs from two components. One is cryptographic hash functions, and the other one is various types of probabilistic proofs that are in fact unconditionally secure. Okay, and by virtue of being unconditionally secure, in particular, they don't rely on any assumptions on the attacker. In particular, it doesn't matter whether it is classical or quantum. Okay, There are bonuses to this framework. You're only making a black box use of these cryptographic hash functions, so they're easy kind of to swap in and swap out as sort of our best constructions of practical hash functions improves. They're already pretty good, but to the extent that they change over time, it's easy to kind of drop and replace them. And also, quite importantly, these post-quantum Zcash SNARGs are transparent, okay? Which means that they do have a setup, it's just public coin, okay? So, and actually, the first SNARG that was built in the 90s actually satisfies this. This is the Micali Construction, okay? If you've seen it already, I think that's great. I'm gonna briefly go over it so that you have a sense of how a SNARG looks like. In fact, also if you want to try and explain how does a SNARG look like to somebody else, in my opinion, this is the simplest construction you can explain, okay? And it assumes something about probabilistically checkable proofs, but in terms of cryptography that it uses, it's very simple, just hash functions, okay? So I'm just gonna take this opportunity to kind of present the construction again to you, and then I will mention something about its post-quantum security. So this construction, you can actually think about it as a transformation. It takes as input a type of probabilistic proof called probabilistically checkable proofs. So here's the picture of probabilistically checkable proof. You have a prover and a verifier, okay? And it envisages not short proofs, but actually rather very long proofs, okay? These are proofs that are whose length is polynomially related to the length of the computation that you're trying to check, okay? These are enormous proofs, okay? But they have this a feature that despite being enormous, when you want to check them, you don't have to read them in full. You can just use a query algorithm that spits out a few queries, samples a few locations of the proof, gets back the answers, and decides what to do. Okay? And kind of this verification procedure is SNARG-like in a sense that it sees very little information and it makes up its mind very fast. Okay? Has this kind of succinct properties. And if you're trying to kind of map this notion to a SNARG, it's going to be a little bit difficult because if you just ask the prover, hey, I'm interested in these locations, would you mind telling me what's written in these locations? Actually, the prover can cheat you. So it's actually important you first write down the proof independent of the query locations, okay? So somehow security can be broken if you're trying to use a PCP like in some sort of protocol, okay? You have to first commit to the proof. Nonetheless, this type of construct exists unconditionally, okay? We can construct this type of proofs for any computation. And the Micali construction that I was mentioning takes this and turns it into a SNARG using just hash functions, okay? And can be done in one slide. It's just a very simple picture. I'm going to denote with a little blue square what it's called a random oracle, which is an idealization of a cryptographic hash function such as SHA-256 or Blake. And the way it works is that the SNARG prover will imagine in its head writing down a PCP proof. Now, because the verifier can't believe the thoughts of the prover, he is going to further commit to this proof using a Merkle tree, using the random oracle, the hash function, use the root of the Merkle tree to derive some randomness for the query sampling procedure, sample the queries, figure out authentication paths to certify the answers against the root from which the randomness was derived, and package all of this into a tiny proof that is then shipped off to the verifier, who can then independently go ahead and say, yes, these paths are certifying the answers to the queries against the root of the Merkle tree, and yes, the answers that you provided me make the decision predicate accept. Okay? So this is a construction of a SNARG using a PCP. Okay? It's the main step that cryptography helped us with is to force the prover in his own sort of mind to commit to the PCP before the queries are sampled. Why? Because the PCP needed that. That was being the case. This construction is very, very lean in the sense that the time of the SNARG prover is essentially the time of the PCP prover. The time of the SNARG verifier is essentially the time of the PCP verifier, up to very simple and very cheap hashing. This is unlike, for example, what happens in pairing-based SNARGs, where cryptography takes most of the computational cost through multi-exponentiations. Here, the hashing is blazing fast and linear time, very, very fast. So most of the cost really just falls down onto the PCP construction. The proof is small because you're only communicating a small number of queries that you're actually interested to look at together with authentication paths whose length is logarithmic in the length of the proof, right? All right, so this is the Micali Construction. This is the first construction of a SNARG ever, okay? It was introduced by Micali, building on work on Killian in the 90s. And in a classical setting, what we know about this construction is that it is we can prove that it is unconditionally secure in the so-called random Oracle model. This is saying assuming that the hash function that we're using to compute this Merkle tree and derive the randomness is perfect, behaves like a random function, then the entire thing is actually unconditionally secure. And if you care about a proof of knowledge or zero knowledge, these are kind of two important properties for ZK SNARG, then these can be taken care of. They're basically inherited from the underlying PCP. So you just need to make sure the underlying PCP construction has these properties. So I'm actually here to announce that we have a new theorem with two of my students, Peter Manohar and Nicholas Spooner. And we've been able to formally prove that this construction is unconditionally secure in the so-called quantum random Oracle model, okay? So to this day, we have it's referred to as constructions such as the Micali construction as plausibly post-quantum because we're not aware of any attacks on these constructions. However, now we can actually go ahead and formally prove that they are in fact post-quantum, so supporting our belief using a security reduction. Just to tell you briefly, I'm not going to talk at all in any technical detail about the result. I'll just mention what is the quantum random Oracle model. This is basically saying that you allow the adversary to evaluate the oracle in superposition. Okay, so basically the attacker has access to an ideal hash function, a random function, which it can evaluate in superposition. Okay. And it's actually a very tricky model to work with. It was introduced about 8 years ago, and it is the gold standard for analyzing post-quantum security for hash-based cryptography, really. So, for example, if you're interested in post-quantum security and look up many of the submissions to the NIST call for post-quantum cryptography, a lot of the sort of submissions go ahead and try to understand, say, the security of digital signatures, against quantum random oracles. But now we know this is the Micali construction is post-quantum secure, and our analysis actually gives you tight bounds up to small constants. So you could even set your security parameters to take into account the power of quantum, and actually you can actually set security parameters in the real world to be post-quantum secure. Okay, so the Micali construction has many good things. At this point, it's post-quantum. As I was mentioning earlier, we already know that it makes a black box use of lightweight cryptography. It's transparent. So what are bad things? Well, first, we're using a random oracle, but as practitioners, we don't really care too much. The main problem is that PCPs are rather expensive. And actually, in work with Ailey, like a number of years ago, we were able to make PCP constructions, not that expensive, but they're still pretty expensive. So at this point, we are left with the question, okay, we have post-quantum ZK SNARGs, but do we have any efficient post-quantum ZK SNARGs, okay? Because, that would be nice, right? Because we care about post-quantum security, not just in theory, but also because we want to build a sort of blockchain infrastructure with post-quantum ZK SNARGs. So let me tell you about efficient post-quantum ZK SNARGs. So again, in a line of works with Eli and some of our students in the last few years, we've been studying constructing ZK SNARGs, also known as STARGs, such as the ones that were discussed earlier today in Eli's talk that are underlying the STARGDEX engine, using an extension of PCPs known as interactive oracle proofs. Okay, and I will tell you that this type of construction is also post-quantum. Okay, so let me tell you about this. So interactive oracle proofs are actually rather simple types of probabilistic proofs in the sense that they're merely a multi-round extension of the notion of a PCP. So before, the prover would just send a long proof that the verifier would probabilistically sample at a few locations. Now we're just considering protocols where this happens over multiple rounds. So over multiple rounds, the verifier maybe sends some challenges, the prover replies with these long proofs. At some point, the verifier is done interacting with the prover, and it will just sample a few locations of these very long proofs, okay? And get back some answers and decide, okay? And in this case, kind of the verifier you can think about has a lot more freedom in terms of things it can do, okay? It can simultaneously leverage notions of randomness, interaction, and probabilistic checking, okay? And there's a construction that takes these types of probabilistic proofs and turns it into a SNARG. There's actually a construction I introduced with Alien, one of my students, Nick, a few years ago. And again, it's a rather simple construction to understand. Basically, we're going to do some sort of iterated Micali. The prover imagines the first sort of long proof in his head. It will commit to it with the Merkle tree. And then it will kind of stick it into a hash chain that keeps track of all rounds and sort of incorporates any roots that are committing to the various proofs that are encountered during the interaction, okay? And because the interaction is public coin, you can always derive randomness for the verifier sort of along the way, like you did before earlier in the Micali construction. So when you're done with the interaction simulated in the prover's head using Merkle trees and a hash chain, you would sample the queries, get back the answers, and now send off a small proof that incorporates all the roots and the authentication paths against them. Like before, the verifier would check the answers, certify against the roots. The roots are in a hash chain, meaning that kind of the order of rounds was respected, and that the answers are checked. Okay? So this is just, to some extent, a rather natural extension of Micali construction to the case of interactive oracle proofs, which you can think about as multi-round PCPs. Again, here, like in the Micali construction, there is nothing going on other than using cryptographic hash functions. There is no use of algebra, there is no use of discrete logarithms, no lattices, nothing, okay? We're just using some generic, sufficiently strong hash function, or really a random oracle. Like before, we have been thinking that these types of constructions are plausibly post-quantum secure. And now I'm happy to announce that we have, in the very same paper that should go online next week or the week after, very soon, we've been able to prove that this construction is also post-quantum secure in the quantum random oracle model. Okay, so that formally this construction is really secure against quantum adversaries. And so this is just like in the Micali construction, and like in the Micali construction, the efficiency of the proving and verifying is tightly related to the one of the IOP. It's a transparent proof system. We're still using random oracles, but now efficiency is unlike before, in the sense that in the last few years, we've made a lot of progress in constructing interactive oracle proofs that are much, much more efficient than PCPs. So the line of works here that sort of started again a few years ago, and it is ongoing. It's a really exciting and active research frontier. There's many techniques that were introduced, and sort of the much-proved efficiency of IOPs has enabled things, for example, Stark decks that you have seen to date. And underneath it all, there is an efficient construction of interactive oracle proof. So I'm leaning towards the end of my time, so I just want to summarize what I talked about today. I talked about post-quantum ZK SNARGs, and specifically I told you that we have a generic framework to construct post-quantum ZK SNARGs. It involves combining cryptographic hash functions, specifically modeled as random oracles, and a type of heuristic proofs known as interactive oracle proofs. To the best of my knowledge, this is the only approach that gives rise to a publicly verifiable, asymptotically efficient ZK SNARGs that are post-quantum. And I would like to encourage the community to study post-quantum ZK SNARGs either through additional approaches, perhaps based on lattices, or through this approach, because interactive oracle proofs is a rather new notion. We've been working on it for a number of years. There is still a lot that can be done there, and any progress in the efficiency of interactive oracle proofs is progress that I think will be reflected for many years to come, in a sense that these types of constructions, as far as I'm concerned, they're indestructible. Not only they're post-quantum secure, but they're using such little cryptography and such bare bones cryptography that it's just, I can't imagine any situation in which they could be attacked. So any progress that we make on these as a community will kind of benefit so generations hence. If you want to play with this framework, we have a code base out, and you can go to libiop.org, and there is this generic transformation is implemented and instantiated for a number of protocols that we've published. That's all I wanted to say, and I'll take some questions. I can, of course. Oh, yeah, please. But you can also take a picture of me if you want. I'll stay here. Thank you. Okay.
Hey, thank you. So it's my understanding that these authentication paths actually contribute a significant amount of length to the size of the proof.
They sure do.
Is there, like, do you have any ideas at all for how to counter this?
Yes.
It seems unavoidable.
It's unavoidable, but it's mitigatable in the sense that right now, the reason that we have many authentication paths to deal with is because we're amplifying the soundness of the underlying PCP or IOP by repeating queries multiple times. And so each time you repeat the query, your query lands in a different part of the Merkle tree, and now you have many authentication paths. This need not be the case, in a sense that, at least theoretically, it is plausible to construct IOPs or PCPs, but in particular IOPs, where each symbol that you're reading from the proof actually carries more information than, say, one field element. It carries maybe a tuple of field elements. And this goes in the area of something called the sliding scale conjecture, okay, which basically postulates that it is possible to construct, say, PCPs or IOPs, where if you read just a small constant number of symbols from the proof, and each symbol has size security parameter, that's enough for security parameter soundness. In such a case, you would naturally not have to read lambda many authentication paths, but a small constant number. In such a case, back-of-the-envelope computations show that you could probably go on the order of 1 kilobyte proofs. Yeah.
So is there any hope of coming up with like a better accumulator than a Merkle tree that might have shorter?
People have already done that, and there are trade-offs. So there are these accumulators based on RSA-style accumulators and class group-style accumulators. They're not post-quantum, but as pre-quantum alternatives, they give you these trade-offs where the prover becomes more expensive and the proof becomes smaller. It's an interesting question to come up with post-quantum accumulators that give you similar trade-offs.
How would you compare this to something like Zcash?
Good. Both of these constructions are post-quantum because they only make use of hash-based constructions. The main comparison is a trade-off in prover time versus proof size and verification time, really. In Zcash, the prover time is linear, okay? It's very fast. It's something you can also stream, okay? In most efficient constructions of IOPs, at best, the known provers are n log n arithmetic complexity. In particular, this is coming from fast Fourier transforms that will take up your space. So where your prover needs to be very fast, Zcash might be a better choice, but you probably cannot run it on large enough circuits because your proof size are going to be very, very big. It's linear, okay? Whereas for these constructions, you can get very tiny proofs, polylogarithmic, and very tiny verifiers. And typically, we're not that concerned with the prover because, for example, with the application that we mentioned today, the SNARG DEX is just some giant prover sitting somewhere, acting as a service infrastructure for the rest of the world who benefits from small proofs and fast verification.
So this theorem on the quantum model, say it's really a PCP or IOP that you just, from the sliding scale, you just read one big thing.
Yeah, or two big things, yeah.
Yeah, is it more sensitive in that case? Like, does it, in terms of concrete numbers, or it doesn't care if it's reading a lot of bits or one big thing?
No, the concrete numbers certainly matter. If we had an IOP with a constant number of queries, each of which has size lambda, and it gives you soundness 2 to the minus lambda, the concrete constant number of queries that you read will certainly matter. If it's 10, 20, a million, right? So
no, I'm saying like the reduction from the IOP to like a
it doesn't care
if it's one big thing or